Welcome to our discussion on matter and energy. This is going to be about pure substances and mixtures. And so there's three essential questions we're trying to answer today. First of all, how can matter be classified? The second question we'll look at is what is solubility? What is a solution? And third, how can mixtures be separated? All right, so let's look at how can matter be classified. There are two major categories of matter. The first one is pure substances. Pure substances are going to be things such as elements or compounds. Elements you can find on the periodic table. Compounds are going to be two or more elements chemically bonded together. The other big section of matter would be mixtures. And there's two types of mixtures. Homogeneous mixtures, in which all of the solution or all of the mixture is exactly the same, and heterogeneous, in which the mixture is going to be different depending on where in the mixture you're looking. So let's look at a couple of examples. Homogeneous mixture, one example is stainless steel. Stainless steel is a solution of chromium and iron that is mixed together to make a really strong metal. So stainless steel is a solution. It doesn't matter where we cut into any of these stainless steel pipes, the steel is still going to have the same amount of chromium and iron no matter where we cut. For heterogeneous, the example I'm giving you is granite. Granite is a type of rock that is made up of quartz and other rock types, and this is heterogeneous because even if you look at this rock right here, depending on where you cut into it, you're going to have different amounts of quartz and different amounts of other minerals that are making up that granite. Elements, an example is silver. Again, elements can be found on the periodic table, so any one of those elements on the periodic table would be a pure substance, and this example is silver. And then finally, we have compounds. An example of a compound that we're well aware of is sugar. And all sugar is going to, well, all table sugar is going to have the combination of carbon, 6 carbons, 12 hydrogens, and 6 oxygens. And it doesn't matter what type of table sugar, how big the grain is, it's always going to be in that ratio. And they're going to be linked together chemically. All right, so let's look a little bit closer. Elements are going to be the simplest kind of matter. They cannot be broken down into any simpler substance. They are always just one kind of atom, and they're expressed in symbols on the periodic table. So we've got a couple examples here. We've got oxygen down here. We've got nobelium, and then here's the periodic table, and I've given you all a copy of that. And as an element, you know, all these circles are the same type of atoms. So if you imagine that these are hydrogen atoms, let's say, all of these hydrogen atoms are going to look and act exactly the same. The other type of pure substance is a compound. And compounds are substances that can be broken down only by chemical methods, and that's because the pieces of a compound are made up of 2 or more atoms that are chemically combined. So it's not like we just mix them up and they form this compound. Instead, those atoms have to chemically bond together. These are usually expressed in a formula made up by the element symbols, and one that we all know, of course, is water's compound is expressed by the formula H2O. Once again, if we take a look at kind of a diagram of our compounds here, the circles represent one type of atom, and we'll call these hydrogens. So all the blue ones are hydrogens, and then the green ones, the green ovals here, let's call them oxygens. And so it doesn't matter what molecule, what compound you look at, they are all exactly the same. They have 2 hydrogens and 1 oxygen, and the hydrogens are always linked to the oxygen. They're combined in the same way, and we call that a definite composition. All the material is combined in the same order, in the same way. Combined in same order. So all of those water molecules are going to look and act exactly the same. They're going to have 2 hydrogens and 2 oxygens. Some other examples of compounds you might know are sodium chloride. Sodium would be Na and Cl would be chlorine. Together they make up sodium chloride. And then, like we said, water, we have 2 hydrogens, 1 oxygen, making dihydrogen monoxide, otherwise known as water. The other big umbrella that we have for mixtures is, or for matter, is mixtures. So mixtures are going to be a physical blend, no longer a chemical blend, a physical blend of at least 2 substances. And because we have a blend, it could have a variable composition, meaning it's going to change. And even if we had, say, a mixture of sugar water, if we had 2 mixtures of sugar water, so there's my sugar, and I had another one, and we imagine that there was the same amount of water, but this one had twice as much sugar. So I'll put 2 sugars here. That's certainly possible, and so now these 2 mixtures, even though they're both sugar water, have a variable composition. They are different from one another. These mixtures can be separated by physical processes, which we'll go over in a few minutes. And remember that mixtures can be either homogeneous, homo meaning the same, hetero meaning different. So homogeneous means the same composition throughout. It's going to be a uniform composition, kind of like our sugar water. And then heterogeneous means a different composition throughout, or not uniform. So something in which it depends on where we are in that mixture, it's going to look a little bit different. So here's a picture of a homogeneous mixture, and you can see that all the different compounds here, the circles and the triangles, are evenly spaced about. They're mixed together so that everything is evenly mixed, and that's what a homogeneous mixture is. Everything is going to be perfectly evenly mixed. If we take a look at a heterogeneous mixture, now it depends on what part of the mixture we grab. So if I grab this mixture right here, and then I grab this right here, what I'm grabbing is essentially the same amount of matter, but I've got very different compositions. In this one I've got 4 yellows and 2 or 3 blues. In this one I have 2 yellows and about 5 blues here. And so even though I'm taking about the same amount of liquid or the same amount of the mixture, it's not evenly mixed. So that is a heterogeneous mixture. Alright, some other examples of homogeneous mixtures. If you make the perfect glass of chocolate milk and it all mixes in, this is called a solution. And it doesn't matter if you drink the very top or you drink the bottom or you drink the middle, it's all going to taste the same because you've made the perfect mixture of chocolate and milk. Tap water, stainless steel, air are all homogeneous mixtures. Heterogeneous mixtures would be things like a tossed salad. Some bites you might get more lettuce than anything else. Other bites, maybe you have a big cherry tomato in there, and so you get less lettuce. It's a heterogeneous mixture. Swamp water, salad dressing are all heterogeneous mixtures. You could probably think up several examples. Here's over on the side here, I have an example of a heterogeneous mixture, and you can see if I grab this right here or if I grab this right here, we're going to have different amounts of each substance. Alright, so let's take a look at contrasting a compound and a mixture. A compound, remember that we have one type of material. In a mixture we have more than one. A compound is a chemical blend of elements. A mixture is a physical blend of compounds, usually, maybe elements, but it's a physical blend. And then compounds have a definite composition. You're going to have equal ratios no matter where you look. Mixtures are going to have a variable composition. Alright, so a special type of mixture is called a solution. And so our second essential question is, what is solubility? And I lost my picture here, but we're going to continue on anyway. So what is solubility? Well, solubility is how saturated a solution is. So solubility measures how much solute can dissolve in a certain amount of solvent. Solute is going to be what we are dissolving. So in this up here, salt would be our solute, and our solvent is going to be what is doing the dissolving. So our water would be our solvent. Usually temperature is going to affect this, so with liquids especially, it increases with temperature, but if we're looking at the solubility of gases, a lot of times that decreases with temperature. So when we're talking about adding more solute to a solvent, how can we continue to do that? Usually what we're thinking about doing is increasing temperature so that we can continue to add more and more solute. There's different levels of saturation. So Kool-Aid many times is unsaturated. It contains less than the maximum amount of solute. And so if you really wanted to, if you make this picture of Kool-Aid, you're supposed to add 1 cup of sugar. I don't know what that is in metrics. But if you wanted to add 1.5 cups, it would probably still work. The sugar would all still mix in. So the 1.5 would be more saturated. This would be less saturated, but this is an unsaturated Kool-Aid. Then we have the saturated. That's going to contain the maximum amount of solute dissolved for a certain temperature. It's going to be just perfect. There's going to be an equilibrium between particles that are dissolving and those that are not. And then we have a supersaturated, which contains more than the maximum amount of solute. And this is what we do when we make sweet tea. If you've ever made sweet tea, you're going to heat up the tea so that you can get more sugar dissolved in that tea. This is a solubility curve. And if we just take a look at, let's say, this blue KCl line, potassium chloride, if we're right on this line right here for this temperature of 50 degrees, that's about, 42 or 43 grams of salt and 100 grams of water. That's going to be our saturation line. So this is perfectly saturated. If I'm below that line on the 50 degree mark, it's going to be unsaturated. If I'm above that line, it's going to be supersaturated. And then finally, and I'm going to go through these very quickly, we have different ways of separating mixtures using their physical changes. You can probably think of some others, but our first one is centrifuging. Centrifuge is a machine that rotates samples at really high speeds and is going to make the more dense part of the mixture end up at the bottom. The less dense will end up at the top. And so then we can separate those a little bit easier. Another way we can do it is by filtering, and so we've done this in the lab. You've probably done it a bunch at home at some point, but you pour things through a filter which has holes smaller than the solid, and so you're going to get the solid in your filter, and then all of the liquid goes down below. So you can do that with pasta and water. And then finally, we've got decanting. Decanting is going to have, again, a more dense part of the mixture down here in the bottom, a less dense up here. So this is less dense, and it is so much less dense that we can just actually pour it off, and that is called decanting. And then the last one I have is something that we've also done evaporation, and we can also call this a distillation. This is where we're separating a solid from a liquid that has been dissolved, and so we get rid of that liquid and the salt